isotopes, as mentioned previously, are something that has the same number of protons but a different number of neutrons. An example of this is lithium. So in the real world, lithium, and on the periodic table we write lithium atomic number 3, and it has a mass number of 7. So it has 4 neutrons. But lithium can also be naturally found as lithium 3,6. So it has the atomic number 3 still, has to because it's lithium. But in this case it has 3 neutrons, not 4 neutrons. The key with isotopes, and an important thing to note, is that these are chemically identical. So they don't behave any differently. They'll react with whatever they react with exactly the same, because changing the neutrons doesn't change the particle at all. All that means is that this is a heavier element. It's more dense. It's got an extra neutron here, so it's going to have a slightly larger mass, and it's going to be a more dense element. But other than that, they're chemically identical. An example of this that you often hear about, and we'll cover later once we get into fission and fusion, is heavy water. Let's look at plain old hydrogen. Hydrogen is 1, 1. Has 1 proton, no neutrons, so its mass number is 1. That is just basic hydrogen. If I then took a hydrogen and added a neutron to it, it's still hydrogen, but it's now got 1 neutron. So it's hydrogen 2, or H2, not to be confused with H2. It would be H2 versus H1. So this is a heavier version of hydrogen. It's still hydrogen. It's chemically identical. It'll react just the same as its twin brother over here, but we've made it heavier. I could go one step further and I could go, well, let's add 2 of them. And I'll have hydrogen 3. Still has 1 proton, 1 proton, 1 proton, but now we've got no neutrons, 1 neutron, 2 neutrons. So these are heavier versions of hydrogen, and we actually name these. So this one we call protium. This one is called deuterium, and this one is called tritium. So these are the names of the isotopes of hydrogen. So deuterium and tritium in particular are often seen in nuclear reactors as your heavier waters. So we can make water with heavy hydrogen, because the hydrogen will react with the water, it'll bond to the water chemically exactly the same between all 3. Except now we can bond a heavier hydrogen to the oxygen, and we've made a heavier water. Hence, again, the creative scientific naming, we call it heavy water. The last important thing to mention is the difference between an isotope and a radioisotope. So we talked about the isotopes of, say, hydrogen. So we have plain old hydrogen, slightly heavier hydrogen, and hydrogen's overweight brother. Heavy hydrogen, which is tritium. The important thing here is that we could have these isotopes and they're perfectly stable. So in hydrogen's case, tritium may be perfectly stable. It's denser and heavier, but it's happy as it is. It's happy being overweight. That's different to something like when we go into uranium and we look at like U-235, for example. That's uranium with a lot more or a lot less neutrons than it would ordinarily have. If we add enough neutrons and we just keep packing it in and packing it in, the glue just gets weaker and weaker. So suddenly it becomes more and more unstable. And when we get to a point where we've got an isotope that is radioactive, that it actually breaks apart and gives off this radiation, that's what we call the radioisotope. So the name kind of spells it out for you. Radioisotope. So you know from this part, from the isotope aspect, that this means we've got plus or minus the neutrons. Something has been added or subtracted. Radio sounds like radiation. So this is about the radiation aspect. So a radioactive isotope, a radiation isotope, is what we call a radioisotope. So that's the difference. An isotope has more neutrons but is not necessarily unstable. A radioisotope is an isotope that is reactive, so it's actually going to decay and it's going to produce some type of radiation.